Hello chemistry students, Dr. Tullis here. In this section we will write the equilibrium constant expression relating concentrations of ions in solution to Ksp for any insoluble salt. We'll calculate the Ksp value for a salt from its solubility and calculate the solubility from its Ksp. We'll recognize how the presence of a common ion affects the solubility of a salt, understand how hydrolysis of basic anions affects the solubility of a salt, and recognize that salts with anions derived from weak acids have increased solubility in acidic solutions. Remember back to precipitation reactions from Gen Chem 1? Precipitation reactions are exchange reactions where one of the products is a water-insoluble compound such as calcium carbonate. I have calcium chloride and sodium carbonate, and they do a double date swap. So calcium is going to ditch the chlorine and it's going to combine with the other anion, and then this cation, sodium, will join with the other anion. So I would have sodium chloride and calcium carbonate. Then we check our solubility rules, which we had a large chart for, and calcium carbonate would be our insoluble compound, which would form the precipitate. Now we want to make our estimates of solubility more quantitative and explore conditions under which some compounds precipitate and others do not. Here's an example of more of those exchange reactions that we covered in Gen Chem 1. We're focusing on our precipitation reaction. And again, we know that when we looked at those products formed, we conferred with our solubility rules. A compound was either soluble, insoluble, or slightly soluble. How do we differentiate between these? Well, the answer lies in equilibrium. It turns out that equilibrium governs the solubility of inorganic salts. Here's an example of lead iodide that is insoluble and it forms a precipitate. Many natural processes depend on the precipitation or the dissolving of a slightly soluble salt. This creates a heterogeneous solution composed of a solid and aqueous ions. When an excess of a slightly soluble ionic compound is mixed with water, an equilibrium is established between the solid and the ions in the saturated solution. Let's look at the salt calcium oxalate, CaC2O4. Here I have my solid salt, and it's in equilibrium with my calcium 2+ ions dissolved in solution and the oxalate 2- ions dissolved in solution. The solubility product constants are used to describe saturated solutions of ionic compounds of relatively low solubility. A saturated solution is in a state of dynamic equilibrium between the dissolved, the dissociated ionic compound, and the undissolved solid. So the extent to which an insoluble salt dissolves can be expressed in terms of the equilibrium constant for the dissolving process of the salt's ion concentrations in solution. We call this the Ksp. And we know that we express any equilibrium constant as products over reactants. Here are my products. I would show the concentration of Ca2+ times the concentration of the oxalate 2- all over the reactants, but notice my reactant is a solid, so we leave it out of our K expression. This special type of equilibrium constant for this process is called the solubility product constant and is given to a solution containing sparingly soluble salts. The Ksp, again, is the solubility product constant, and it's just like any other K. It's the product of the ion solubilities and can be estimated by determining the concentration of the cation or anion when the compound dissolves. It always has the same form, and we are given numerical values of Ksp in your appendix and should be on your cheat sheet. Let's look at lead chloride in solid form. Lead chloride dissociates into lead +2 ions and chloride- ions. There are 2 chlorines on the left, so I need 2 chlorines on the right. So when I write my Ksp expression, I would look up lead chloride, and it would tell me that its Ksp value is 1.9 times 10 to the -5 is equal to the concentration of my Pb2+ times the concentration of my chloride, and that 2 tells me that it is squared. Here are just a few common insoluble compounds and their Ksp values. Notice that they range from -9 to -10 to -11 to -13. And the smaller that KSP value, for example, this would be the smallest value times 10 to the negative 13th. That means that our solute does not dissolve into a lot of the solution. The more soluble it is, so the larger the number, the higher the KSP value it is. Let's relate the solubility and the KSP. Solubility product constants are determined by careful laboratory measurements of the concentrations of ions in solution. KSP values for insoluble salts can be used to estimate the solubility of a solid salt or to determine whether a solid will precipitate when solutions of its anion and cations are mixed. Why don't you pause the video here and practice writing the KSP expressions for these three. This would be for lead carbonate. The KSP is equal to the concentration of our lead plus 2 ions times the concentration of the carbonate minus 2 ions. This would be for the lead chloride, and this would be for the calcium phosphate. Let's try a practice problem here. Calcium fluoride, the main component of the mineral fluoride, dissolves to a slight extent in water. So here's our calcium fluoride in equilibrium with the calcium plus 2 ions and the fluoride minus ions, and there's our KSP expression. Let's calculate the KSP value if the calcium ion concentration has been found to be 2.3 times 10 to the negative 4th molarity. Well, if we're given the calcium concentration, then the fluoride has got to be 2 times that concentration. It would be like if calcium plus 2 was X plus 2X. I have to double that concentration to get the fluoride concentration. So 2 times 2.3 times 10 to the negative 4 would be 4.6 times 10 to the negative 4th. Now I can plug both of those concentrations into my KSP expression. See what you get. Hopefully you get 4.9 times 10 to the negative 11th. How about this one? Pause the video here to try to solve this. I was given the barium ion concentration, so to get the fluoride concentration I needed to do 2 times the concentration of the barium. Then I'm going to plug it into my KSP expression. If I know the barium and I know the fluoride, and then I need to square the fluoride concentration, and you should get 1.9 times 10 to the negative 7. Let's look at the solubility from KSP. KSP values for insoluble salts can be used to calculate the solubility of a solid salt or to determine whether a solid will precipitate when solutions of its anion and cation are mixed. First, we're going to look at an example when we're given the KSP value. Look up on your solubility KSP chart and look up barium sulfate. You will find it has a KSP value of 1.1 times 10 to the negative 10th. Let's calculate the solubility of barium sulfate in water in moles per liter and grams per liter. First, I'm going to set up my ice table because initially I have all barium sulfate and I have no ions. Then we know that we lose reactant and we gain product. And then at equilibrium, again, we don't include any solids in equilibrium, but we know that at equilibrium I would take 0 plus X to give me X and X for both of those cations and anions, and then plug those into my equilibrium expression. We were told that its solubility product constant was 1.1 times 10 to the negative 10 is equal to X times X. So X squared is equal to 1.1 times 10 to the negative 10. Take the square root and we're given the X value. X value is the concentration, which is molarity, and it would be the same for the barium ion and for the sulfate ion in pure water. Concentration is in moles per liter, so I'm going to take that moles per liter and get to grams per liter. But to do that, I have to take barium sulfate and find the molar mass. Add up 1 barium, 1 sulfur, and 4 oxygens, and we should get 233 grams. Multiply across and divide by 1, and I would get 0.0024 grams per liter. So in 1 liter of water, only 0.0024 grams of barium sulfate will dissolve. And it's actually really a great thing that its solubility is so low, because barium sulfate is used to help diagnose or find problems in the esophagus, in the stomach, and in the bowels. and it's a radiographic contrast agent. So it's a good thing that it's not soluble because it could be quite toxic to our system. Let's look at another example. Knowing that the KSP value for magnesium fluoride is 5.2 times 10 to the negative 11, calculate the solubility of the salt in moles per liter and in grams per liter. Let's write out our equilibrium expression and our KSP expression. Then I'm going to make my ice table. We obviously know that solids don't participate in the ice table, but I know that I started with a solid initial reactant and that initially I had no ions. I lost reactant, I gained product. Here I gained X, here I gained 2X. So at equilibrium, I have X and 2X. So I would have X times 2X squared. X times 2X squared. That square is going to distribute. 2 squared is 4, and X squared is obviously X squared. So I would have 4X squared times X is 4X cubed. And 4X cubed is equal to the KSP, which is 5.2 times 10 to the negative 11. We first have to get rid of that 4, so I'm going to divide both sides by 4. That gets rid of this. And then I need to take the cubed root of both sides. And that would leave me with 2.35 times 10 to the negative 4th. And with two significant figures, since I started with 2, 2.4 times 10 to the negative 4th. And that's molarity, moles per liter. That's telling me that that's how many moles of magnesium fluoride dissolve per liter of solution. Now let's figure out how many grams per liter. I'm going to take that information and times it by the molar mass. Add up 1 magnesium and 2 fluorines, and I should get a molar mass of 62.3 grams per mole. That crosses off my moles, leaving my units of grams per liter, and I would get 0.015 grams of magnesium fluoride would dissolve per liter of solution.